Hello and welcome to this session on evolution of mathematics and Euclid of Alexandria. The death of Alexander the Great had led to internecine strife among the generals in the Greek army, but by 306 BC, control of the Egyptian portion of the empire was firmly in the hands of Ptolemy I, and this enlightened ruler was able to turn his attention to constructive efforts. Among his early acts was the establishment of a school or institute at Alexandria known as the Museum. As teachers at the school, he called a band of leading scholars, among whom was the author of the most fabulously successful mathematics textbook ever written, the Elements of Euclid. Considering the fame of the author and of his bestseller, remarkably little is known of Euclid's life. So obscure was his life that no birthplace is associated with his name. Our Euclid, by contrast, is known as Euclid of Alexandria, for he was called there to teach mathematics. From the nature of his work, it is presumed that he had studied with students of Plato, if not at the academy itself. Legends associated with Euclid picture him as a kindly and gentle old man. Ptolemy once asked Euclid whether there was any shorter way to a knowledge of geometry than by a study of the elements, whereupon Euclid answered that there was no royal road to geometry. Euclid and the elements are often regarded as synonymous. In reality, the man was the author of about a dozen treatises covering widely varying topics, from optics, astronomy, music and mechanics to a book on the conic sections. Of what Euclid wrote, more than half has been lost, including some of his more important compositions, such as a treatise on conics. 5 works by Euclid have survived to our day: the Elements, the Data, the Division of Figures, the Phenomena and the Optics. The last mentioned is the Geometry of Direct Vision. The ancients had divided the study of optical phenomena into 3 parts. First one optics, the second one catoptrics and the third one dioptrics. Sometimes ascribed to Euclid is of doubtful authenticity, being perhaps by Theon of Alexandria, who lived some 6 centuries later. Euclid's Optics is noteworthy for its espousal of an emission theory of vision, according to which the eye sends out rays that travel to the object, in contrast to a rival Aristotelian doctrine in which an activity in a medium travels in a straight line from the object to the eye. It should be noted that the mathematics of perspective, as opposed to the physical description, is the same no matter which of the 2 theories is adopted. Among the theorems found in Euclid's Optics is one widely used in antiquity: tan alpha by tan beta is less than alpha by beta if 0 less than alpha less than beta less than pi by 2. One object of the optics was to combat an Epicurean insistence that an object was just as large as it looked, with no allowance to be made for the foreshortening suggested by perspective. Euclid's Phenomena is much like the sphere of Autolycus, that is, a work on spherical geometry of use to astronomers. A comparison of the 2 works indicates that both authors drew heavily on a textbook tradition that was well known to their generation. It is quite possible that much the same was true of Euclid's Elements, but in this case there is no contemporary work extant with which it can be compared. The Euclidean division of figures is significant in that it is a work that would have been lost had it not been for the learning of Arabic scholars. It has not survived in the original Greek, but before the disappearance of the Greek versions. An Arabic translation had been made omitting some of the original proofs because the demonstrations are easy, which in turn was later translated into Latin and ultimately into current modern languages. This is not atypical of other ancient works. The division of figures includes a collection of 36 propositions concerning the division of plane configurations. For example, proposition 1 calls for the construction of a straight line that shall be parallel to the base of a triangle and shall divide the triangle into two equal areas. Proposition 4 requires a bisection of a trapezoid ABQD by a line parallel to the bases. The university at Alexandria evidently was like modern institutions of higher learning. Some of the faculty probably excelled in research, others were better fitted to be administrators, and still others were noted for teaching ability. It would appear that Euclid very definitely fitted into the last category. There is no new discovery attributed to him, but he was noted for expository skill. This is the key to the success of his greatest work, the Elements. It was frankly a textbook and by no means the first one. The Elements, an introductory textbook covering all elementary mathematics, that is arithmetic, in the sense of the English higher arithmetic or the American theory of numbers, the synthetic geometry of points, lines, planes, circles and spheres, and algebra, not in the modern symbolic sense, but an equivalent in geometrical garb. It will be noted that the art of calculation is not included. Proclus described the Elements as bearing to the rest of mathematics the same sort of relation as that which the letters of the alphabet have in relation to language, where the Elements intended as an exhaustive store of information. The author probably would have included references to other authors, statements of recent research and informal explanations. Euclid himself made no claim to originality, and it is clear that he drew heavily from the works of his predecessors. It is believed that the arrangement is his own and presumably some of the proofs were supplied by him. But beyond this, it is difficult to estimate the degree of originality that is to be found in this, the most renowned mathematical work in history. The Elements is divided into 13 books or chapters, of which the first half dozen are on elementary plane geometry, the next 3 on the theory of numbers, book 10 on incommensurables, and the last 3 chiefly on solid geometry. There is no introduction to the work, and the first book opens abruptly with a list of 23 definitions. The weakness here is that some of the definitions do not define, inasmuch as there is no prior set of undefined elements in terms of which to define the others. Thus, to say, as does Euclid, that a point is that which has no part, or that a line is breadthless length, or that a surface is that which has length and breadth only, is scarcely to define these entities, for a definition must be expressed in terms of things that precede and are better known than the things defined. Objections can easily be raised on the score of logical circularity to other so-called definitions of Euclid, such as the extremities of a line are points, or a straight line is a line which lies evenly with the points on itself, or the extremities of a surface are lines, all of which may have been due to Plato. The Euclidean definition of a plane angle as the inclination to one another of two lines in a plane which meet one another and do not lie in a straight line is vitiated by the fact that inclination has not been previously defined and is not better known than the word angle. Aristotle had made a sharp distinction between axioms or common notions and postulates. The former, he said, it must be convincing in themselves, truths common to all studies, but the latter are less obvious and do not presuppose the assent of the learner, they pertain only to the subject at hand. Some later writers distinguished between the two types of assumptions by applying the word axiom to something known or accepted as obvious, while the word postulate referred to something to be demanded. We do not know whether Euclid subscribed to either of these views, or even whether he distinguished between two types of assumptions. Surviving manuscripts are not in agreement here, and in some cases the 10 assumptions appear together in a single category. Modern mathematicians see no essential difference between an axiom and a postulate. In most manuscripts of the Elements, we find the following 10 assumptions. Following the definitions, Euclid lists 5 postulates and 5 common notions. Postulates of Euclid. Here are the postulates. Let the following be postulated. First one, to draw a straight line from any point to any point. Second one, to produce a finite straight line continuously in a straight line. The third one, to describe a circle with any center and radius. The fourth one, that all right angles are equal. And the fifth one is that if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side on which the angles are less than the two right angles. Common notions. The first one, things which are equal to the same thing are also equal to one another. The second one, if equals be added to equals, the wholes are equal. Third one, if equals be subtracted from equals, the remainders are equal. Fourth one, things which coincide with one another are equal to one another. And the fifth one, the whole is greater than the part. Most of the propositions in book 1 of the Elements are well known to anyone who has had a high school course in geometry. Included are the familiar theorems on congruence of triangles, but without an axiom justifying the method of superposition, on simple constructions by straight edge and compasses, on inequalities concerning angles and sides of a triangle, on properties of parallel lines leading to the fact that the sum of the angles of a triangle is equal to two right angles, and on parallelograms, including the construction of a parallelogram having given angles and equal in area to a given triangle or to a given rectilinear figure. The book closes in propositions 47 and 48 with the proof of the Pythagorean theorem and its converse. The proof of the theorem as given by Euclid was not that usually given in textbooks of today, in which simple propositions are applied to the sides of similar triangles formed by dropping an altitude upon the hypotenuse. It has been suggested that Euclid avoided such a proof because of difficulties involved in commensurability. Only in book 5 did Euclid turn to the well-founded theory of proportions, and up to that point the use of proportionalities is avoided as far as possible. For the Pythagorean theorem, Euclid used instead the beautiful proof with a figure sometimes described as a windmill or as the peacock's tail or as the bride's chair. It is to Euclid's credit that the Pythagorean theorem is immediately followed by a proof of the converse. If in a triangle the square on one of the sides is equal to the sum of the squares on the other two sides, the angle between these other two sides is a right angle. Not infrequently in modern textbooks, the exercises following the proof of the Pythagorean theorem are such that they require not the theorem itself, but the still unproved converse. Book 2 of the Elements is a short one containing only 14 propositions. not one of which plays any role in modern time. Yet, in Euclid's day, this book was of great significance. This sharp discrepancy between ancient and modern views is easily explained today. We have symbolic algebra and trigonometry that have replaced the geometrical equivalents from Greece. Proposition 1 of book 2 states that two straight lines and one of them be cut into any number of segments, whatever the rectangle contained by the two straight lines is equal to the rectangles contained by the uncut straight line and each of the segments. AD into AM plus MN plus NO plus OB is equal to AD into AM plus AD into MN plus AD into NO plus AD into OB is nothing more than a geometrical statement of one of the fundamental laws of arithmetic known today as the distributive law. A into H plus C plus D is equal to AH plus AC plus AD. In later books of elements, books 5 and 7, we find demonstrations of the commutative and associative laws for multiplication. It generally has been supposed that the contents of the first two books of the elements are largely the work of the Pythagoreans. Books 3 and 4 on the other hand deal with the geometry of the circle, and here the material is presumed to have been drawn largely from Hippocrates of Chios. The two books are not unlike the theorems on circles contained in textbooks of today. The first proposition of book 3, for example, calls for the construction of the center of a circle. Book 4 contains 16 propositions largely familiar to modern students concerning figures inscribed in or circumscribed about a circle. Of the 13 books of the elements, those most admired have been the 5th and the 10th, the one on the general theory of proportion and the other one on the classification of incommensurables. The discovery of the incommensurable had threatened a logical crisis which cast doubt on proofs appealing to proportionality, but the crisis had been successfully averted through the principles enunciated by Eudoxus. We have seen that Euclid put off their use as long as possible, and such a relationship among lengths as x is to a is equal to h is to e would be thought of as an equality of the areas Ex is equal to Ah. Sooner or later, however, proportions are needed, and so Euclid tackled the problem in book 5 of the elements. Having developed the theory of proportions in book 5, Euclid exploited it in book 6 by proving theorems concerning ratios and proportions related to similar triangles, parallelograms and other polygons. Book 6 contains in propositions 28 and 29 also a generalization of the method of application of areas for the sound basis for proportion given in book 5 enabled the author now to make free use of the concept of similarity. The Elements of Euclid often is mistakenly thought of as restricted to geometry. We already have described two books, book 2 and 5, that are almost exclusively algebraic. 3 books, 7, 8 and 9 are devoted to the theory of numbers. The word number to the Greeks always referred to what we call the natural numbers, the positive whole numbers or integers. Book 7 opens with a list of 22 definitions distinguishing various types of number, odd and even, prime and composite, plain and solid, that is, those that are products of 2 or 3 integers, and finally defining a perfect number as that which is equal to its own parts. The theorems in book 7, 8 and 9 are likely to be familiar to the reader who has had an elementary course in the theory of numbers, but the language of the proofs will certainly be unfamiliar. Throughout these books, each number is represented by a line segment so that Euclid will speak of a number as AB. Hence, Euclid does not use the phrases is a multiple of or is a factor of, for he replaces these by is measured by and measures respectively. That is, a number n is measured by another number m if there is a third number k such that n is equal to km. Book 7 opens with propositions related to theory of numbers, which today is known as Euclid's algorithm for finding the greatest common divisor. Proposition 8 states that if an is equal to bm and en is equal to dm, then a minus e of n is equal to b minus d of m. Proposition 24 states that if a and b are prime to e, then ab is prime to e. The book closes with a rule, proposition 39, for finding the least common multiple of several numbers. Book 8 is one of the less rewarding of the 13 books of the Elements. It opens with propositions on numbers in continued proportion, geometric progression, and then turns to some simple properties of squares and cubes. Book 9, the last of the 3 books on theory of numbers, contains several 10 theorems that are of special interest. Of these, the most celebrated is proposition 20. Prime numbers are more than any assigned multitude of prime numbers. That is, Euclid here gives the well-known elementary proof that the number of primes is infinite. The proof is indirect, for one shows that the assumption of a finite number of primes leads to a contradiction. Let P be the product of all the primes assumed to be finite in number, and consider the number n is equal to p plus 1. Now, n cannot be prime, for this would contradict the assumption that p was the product of all primes. Hence, n is composite and must be measured by some prime p, but p cannot be any of the prime factors in p, for then it would have to be a factor of 1. Hence, p must be a prime different from all of those in the product p. Therefore, the assumption that p was the product of all the primes must be false. Book 10 of the Elements concerned with a systematic classification of incommensurable line segments of the form a plus or minus root b, root a plus or minus root b, square root of a plus or minus square root of b, and square root of root a plus or minus root b, where a and b are of the same dimension, are commensurable. Today, we would be inclined to think of this as a book on irrational numbers of the types above, where a and b are rational numbers, but Euclid regarded this book as a part of geometry rather than of arithmetic. Book 10 contains 115 propositions, more than any other, most of which contain geometrical equivalents of what we now know arithmetically as surds. The material in book 11 containing 39 propositions on the geometry of 3 dimensions will be largely familiar to one who has taken a course in the elements of solid geometry. Again, the definitions are easily criticized, for Euclid defines a solid as that which has length, breadth and depth, and then tells us that an extremity of a solid is a surface. The spurious book 15 also deals with the regular solids, showing how to inscribe certain of them within others, counting the number of edges and solid angles in the solids, and finding the measures of the dihedral angles of faces meeting at an edge. The Elements of Euclid not only was the earliest major Greek mathematical work to come down to us, but also the most influential textbook of all times. It was composed in about 300 BC and was copied and recopied repeatedly after that. Let us summarize the main points we have discussed so far. This content deals with the significant contributions of Euclid of Alexandria. Elements as a whole is a collection of 13 chapters, each of which has its own importance. Theory of numbers along with prime and perfect numbers are explained through various chapters. Theory of proportion, solid geometry, etc. are the other important topics. It can be concluded that the Elements is an introductory textbook covering all elementary mathematics. Now you can attempt to answer the questions given here. First one, what are the postulates of Euclid? Second one, what is the contribution of Euclid to the development of mathematics? The third one, can you provide all the details of the proof of the Pythagorean theorem by the windmill method? Now you can go through the books for reference. A History of Mathematics by Carl B. Boyer, John Wiley and Sons. A History of Mathematics by Florian Cajori, Macmillan and Co. The Calendars of Ancient Egypt by Parker R.A., University of Chicago Press. History of Greek Mathematics by Heath T.L., Oxford, Clarendon. Hope that you have enjoyed this session. We will meet again with another topic. Thank you for watching this program.